This information is brought to you by Charles Sturt University.
Just speaking out the assignment, lots of people did really good jobs. There was no one got full marks, but people got really close to that. So the weakest question was question 3, the 2 proof questions. I'll talk about that either today's lecture or tomorrow when there's natural break. So what we were doing last week is looking at counting. So how many different options we have for various circumstances. And then in the very last lecture, Tuesday last week, we started talking about probabilities, which is one way of thinking of an application for that. So we're looking at different ways of combining probabilities together. So we looked at and or. So another way of sort of doing probability is what's called a conditional probability. So this is what we're finishing up with. So the way we write that down formally is the probability of A given B. So that vertical line you can see there, just read as given. And we did one example, I think it is. And again, you've seen them before at school. I'm pretty sure you have, but without that fancy notation. So you may not realise you've seen it before. And then we did example about gender ratios.
Not yet. That's good.
We did this one. So, guys. The reader comes up. So the way to work out conditional probabilities often is just to think through it naturally. So we did an example using a two-way table. You can actually just work it out as going the number of options I want to consider, this particular case, well, all options I want to consider blah. And that sort of works out generally. But the way of probability of A given B, the way to do it is to go, well, all the cases I really want to consider are B. That's my global area. So therefore, what I ever put on the bottom of the fraction should be all the options I want to consider. So it's probably B on the bottom. And then on the top, I want A to happen, but B is happening as well. So I want A and B. That's sort of a formula work at conditional probabilities. So there's formulas if you need it, but often you can just work it out just by thinking through it in a given circumstance. And other times, and you've seen this is how you've more seen them at school if you did them at school, is sometimes you can work out the conditional probability directly given a circumstance. And I'll show some later for you. So what you can do with this formula is you can rearrange it. So various different rearrangements give you various useful stuff. So one case where there'd be a probability of A and B, then would be the product of A given B times by the probability of B. Or actually more likely to say the other way around, probability of B times by the probability of A given B. Since we read left to right. So you can rearrange those sort of forms. So what we see here is the probability of A and B, so A happening and then B happening, when I think of it that way, is in general not just a simple multiplication of PB and PA, it can be a little more complicated than that. So the general multiplication rule for AND is multiplication, that is true, but the rule is more complicated. So what we like to do is we like to get to special circumstances where that collapses, and we'll look at that in a second. But let's just deal with this particular formula we have it out in front of us right now. Just see what it means. So it just says the probability of A and B is the probability of getting B first times by the probability of A if we know that B is true. So here's an example. So, made up example, but gives the idea. So, 40% of Saturdays have fine weather, and if we know that Saturday's a sunny day, like it was this weekend at least, then there's an 80% chance that Sunday is also fine weather. What's the probability that any given weekend, both the Saturday and Sunday are both fine? So Saturday, fine, and Sunday, fine. That's essentially what we're trying to work out. Any ideas how to do it?
Wouldn't it be the probability of Saturday being fine multiplied by the probability of Sunday being fine?
Okay, so we don't. What's the probability that Sunday's being fine? And the answer is we don't know. We're not actually told that explicitly. What we're told is just the connection between the two. So we're told the probability that Saturday is fine. We know that one. And what's that equal to?
40% of 0.4.
So 0.4. The other thing we're told is the probability that Sunday is fine if we know that Saturday is also fine. So that's the other number we're told. So the probability that Sunday's fine given that Saturday's fine. So the probability that it continues to be a good weekend, you want to put it that way. What's that probability there? Just read
80%.
80%, yep. So they're the two numbers we've been given essentially. What do we do with those two numbers?
Multiply them.
Multiply them.
So what you just
said, yeah.
Which is what you said. What I wanted to clarify is that this probability here is not the general probability of Sunday being fine, but it's the linking one, or the conditional probabilities that fancy way of putting it. So you multiply those two numbers together, you get 0.32. How would you write that down? How would you communicate that to people?
32.
So you can write that you could write it as just like it is, or you can write 32%. That's also acceptable. So same thing, interchangeable.
Wait, didn't you say that you wanted it as decimal form rather than percentages in the exam?
In your assignment, it's going to be marked by a computer, and therefore that's going to have to be decimal just for standardisation. If you're trying to communicate to other people, what do people understand better?
Percentages.
Probably percentages. So on the audience, normally percentages is people can swallow more than anything else. But they're the same, and they just...
Okay.
So you guys, beyond that, you can go between them more quite happily, I hope. But percentages normally, most people, more people understand percentages than anything else. Particularly compared to fractions. I think fractions is the other option. Fractions is probably the least understood of all the different choices. So that's just an example of that conditional probability of how it links from one to the other. We'll see a few more as we go on. So that gets annoying. So we like special cases. So they're the two sort of forms we have for unions and intersections, or ors and ands. So the probability of A or B is PA plus BB minus the joint one. And we just did the general multiplication rule, the second one there. What we like to do is we like to look at special cases which simplify those formulas down considerably. And then we like to exploit those special circumstances whenever we can. And indeed, if you don't need probability before, you did this all the time. Maybe about realising what the special cases were. So the first one is called mutually exclusive. And because it's all based on sets, you can also talk about it being disjoint. So it's pretty much, we have two events are mutually exclusive if they can't happen at the same time. So putting it various ways, the probability of both of them happening at the same time is 0. So in terms of sets, that would mean that the two sets don't overlap. So the intersection of the two is the empty set. So in that particular case, the OR probability just becomes a straight plus. So if you look at the previous formula on the top here, if we make sure that probability of A and B is 0, that just disappears and becomes much easier to deal with. So pretty much, if you're trying to do OR things, if you're just doing OR stuff which are mutually exclusive, I have no overlap law, makes it much easier. We saw that idea last week, really, when doing counting in general, when you're trying to split up all the different or cases you have for counting, it's much easier if all the options are completely separate from each other. And what I mean by that is they're mutually exclusive. So it just makes it easier to split cases up. And you do each case separately and then just add up the results. So we do that quite naturally in many circumstances. So same thing here too. Can you give me an example of mutually exclusive events? Make it practical. There's lots and lots and lots of answers possible.
Batman and Bruce Wayne being the same.
Oh, that's a good one.
Okay, yep.
But what if when, because Bruce Wayne retires, right? They have a new Batman.
Okay, so different example.
Could you say something like a set of traffic lights when on an intersection like that where the sun's green, this one has to be red? So like they both can't be at the same time, but one can and the other can.
So it's easier to pick on one thing, make it simple. So one traffic light can either be red or green, never both. So the problem.
Okay.
So in a real traffic light situation, you don't want to have accidents generated. So you want to make sure if it's green in one direction, you want to make sure it's red in all the others. That's not mutually exclusive. They should happen at the same time.
Yeah.
What you want to say is if it's green going north-south and green going east-west, they should not happen at the same time. They should be mutually exclusive. Otherwise, you've got a bad set of traffic lights, essentially. And therefore, they used to insist for those traffic lights that you have to be able to prove your program would never generate those sort of circumstances. I'm not sure if I get quite what the procedure is nowadays, but I presume that's the same sort of thing. You don't want to have accidents happening. They used to do them in assembly language and therefore prove it can never be done. No mistakes happen. I think we're relying a bit more higher level logic now. So, simple question. When you're rolling a six-sided dice, what's the probability of getting a 1 or a 6?
It'd be 2 out of 6, wouldn't it?
Okay. So there's a 1 in 6 chance of getting a 1, a 1 in 6 chance of getting a 6. Add them together, usually 2 and 6. And as people worked out, you can do it much quicker than that too, of course. But that's the idea of mutually exclusive. You just do them separately, chuck them together. 1 plus 1 equals 2 essentially is the main mathematics you have to do in that case. So the other one, so mutually exclusive makes sense. You can just sort of see it working. The other one is the idea of independence. So we say two events are independent if the outcome of one does not have an impact upon the other. So I'll say that again. Two events are independent if the outcome if it happens or not, does not have an impact if something else happens or not. That's the interpretive example. That's what it sort of means in practice. Mathematically, it's sort of defined by any three of those rules just given there. The top one being the most easy one to use, and that is the probability of E and F is given by a product, just the product of the two probabilities. So that's what it means mathematically, but in practice it means that the outcome of one doesn't have an impact upon the outcome of the other. So, and what it means is another way of putting it, the probability of E given F is equal just the probability of E. So it doesn't matter if F is true or false, the probability of E doesn't change at all. That's what the second line's trying to say. That's the sense of being independent. Well, this one here is the probability of F given E. It doesn't matter if E is true or false, the probability of F still remains the same. That's the sense of them not being impacted upon each other. So that's the formulas. Let's do some examples, just to try to think through it. You roll 2 dice. The first event is getting a 6 on the first dice. The second event is you get a 6 on the second dice. Are those two events independent or not?
3 goals.
Yes, they are.
Yes, because what you roll on the first roll doesn't change what you get on the second one.
Yeah, that's right. So what you're on the first has no impact upon the second, so yes, they are indeed independent. And so many situations we have, there are independents, and independents are all the really nice formulas. So that's good. What about the second case? So picking, you got a bag of 4 balls, 3 of them red, 1 white. You're picking 2 of them out. The first event is you're getting a red ball on the first ball, you pull out, and the second event is you pull a second ball, and you also want that to be red. Are those 2 independents?
You put the ball back.
No, because you're pulling 2 balls out, you're not pulling one out.
Okay, so let's make no replacement, which is the question someone asked. Yep.
They are not independent, because once you've taken one out, the probability of getting another red one reduces.
Change.
So the odds change depending if the first ball's red or white. The probabilities change, and so there's a dependency there. So your chance of getting, if the first ball you pull out is red, you're less likely to pull out a red ball the second time. There's less red balls to pick from, essentially. So there's a dependency there. So again, and you can see the word just makes sense, hopefully, if you can do it fairly intuitively. What about the last one? You got a hat full of 30 different people, your names essentially.
Oh, yeah, just people.
Sorry, the names.
That's a big hat. 4 people. Awesome.
Okay, the names of 30 people put in a hat, and you pick out 2.
Okay, that's my call.
You wish. So the first event is the name you draw out. The first name you draw out. The second event is the second name you draw out, and you make it more precise if you want to. Are those independent or dependent?
Because you're changing the.
You are changing the odds, but
The first one didn't.
the like you still have the same names in there. You know, there's no overlap of names basically, so it's a bit of a weird one.
You're still changing the percentage chance of pulling it because there's less options in there.
Okay, so when you pull the first person in the hat, you're not putting them back in.
No.
That's the big deal. If you put them back in, they're independent. It's the fact you're not putting them back in is where the problem comes in. So if you're not putting them back in, you've got 1 in 30 chance of picking someone the first time, and the second time you've got a 29 people to pick, 29 names to pick from now. So there's only 1 in 29 chance of picking an individual person. So the probabilities are changing, however you want to put it. So yes, there is a dependency, because whoever's picked second can't have been picked first.
Yeah.
That's the dependency. So the difference between the first one and the second 2 is the first one you're allowed to get the same number happening more than once. So you get 6s, both times. For the second 2, you're not replacing it. So when you're making a second selection, you haven't put the ball back in beforehand. That's the big difference. And so most of the time we'll like to have independence where we can, because it produces much easier to formula, much easier things to deal with. But that's not reality. There's some things that have dependencies there, and we just need to deal with them accordingly. So now we've identified them, let's do some questions. Some are easier than others.
Oh, that's nice.
Okay, so this is back to the dice rolling. Okay, so we've got what's the probability of getting those 2 events happening? What's the probability of getting 2 6s essentially?
You multiply yes, 160, 160, 136.
Okay. Now we said these were independent of each other, so therefore we just work at each dice separately. So what's the probability of the first dice? 1 6. Probably the second one.
6.
And because they're independent, you just multiply them together, and you get, as you quickly said, 1 over 36. And because they're independent, you can do it very quickly. So independence is nice in that circumstance. Again, they're the one, and that's the situation you want to try to manufacture if you can. So you want to try to make sure things are independent when you can. So this is pulling balls from a hat. So we have the 3 red balls in our one white ball, and we're just going to pick 2 balls out from a hat. We want to make sure we get 2 red balls, essentially. So let's do the first one. What's the probability of getting 2 red balls?
So we
Lots of ways of doing it. All the way.
3/4 on the first one and 2/3 on the next one.
Okay, so one approach is the way the direct approach, like this one. And so you've got, for the first ball, 3 of the 4 possible balls you can pick from would be red. So you have a 3/4 chance to be your red ball the first time round. The second time, the probabilities change. It's not the same probability, so you have to work it out brand new. You have to work it probably all over again. So what's probably getting a red ball the second time?
2/3, because there's now only 3 balls in there.
So there's only 3 balls to pick from, and only 2 of the remainers are red. So in terms of what we've done, that's a probability that first one is red. And this second thing we worked out, 2/3, in terms of symbols we've got, that's a probability that the second is red, given the first is red. So the 2/3 there is the conditional probability. So it's the conditional probability of the second one being red, given the first is red. So you may have done examples like this at school. So that second number is a conditional probability, and you put symbols next to it. And you don't need to put symbols next to it for this one either, but I just want to link it to what we just said. What does that simplify down to in this case? Type in your calculator if necessary. What number do you get?
6 balls.
Half.
Half or 50%. Okay, so that's one way of doing it. So that's what I guess call the direct approach. Let's think of other ways of doing it, just to see some alternative methods. You can do it using combinations, which is maybe quicker. I guess you can be the judge if you like which way you like in the end. So, how many different options are there all up? So we've got 4 balls, we want to pick 2 of them. How many different ways are there of picking 2 balls from 4?
That's 4 choose 2.
Yeah, so it's just 4 choose 2. Because we don't care about the order, really. So at the end of the day, you're just going to pick a bunch of balls out. So 4 choose 2 different ways of picking the 2 balls from 4. Now we want to make sure we get 2 red balls. That's our goal. So how many different ways are there of picking 2 red balls from our selection?
2 choose 3. Sorry, 3 choose 2.
So you got to pick 2 from the 3 red balls. How many of the white balls are you picking?
None, so it'd be
It's
1 choose 0.
1 choose 0, if you want to put it that way. What's 1 choose 0 going to be, you reckon?
It's 1, because
It's 1, yeah.
one way of doing it.
There's only one way of picking nothing, essentially. So that's another way of doing it using combinations. And if you do chuck this in your calculator, 3 choose 2 is equal to, you can do it, okay, practice.
3.
So 3, 1 choose 0 is 1, and 4 choose 2
It's 6.
is 6. Which gives you the same answer of a half, or 50% like before. So they give you the same answer, which is reassuring. Who liked the first approach?
It's easier here because we've got smaller numbers.
Who liked the second approach? No one, okay. Sorry, for the people on the video, not everyone voted, but most people picked the first option. Now, if it was just too big, if I said, what's the probability of getting, if you had a bigger case and you had to pick 10 red balls from a much bigger pot, then using the combinations approach might be more efficient. But at the end of the day, you're the one who has to do the question, so you pick the one option you find easier to do. Okay, let's just try the second of these cases here. So we want to know what's the probability of getting 1 red and 1 white. So otherwise the same scenario. Different ways of doing it. Any ideas?
It'll be 3 choose 1 times 1 choose 1 over 4 choose 2.
Okay, so let's do different approaches. Let's do combinations. So the combinations approach is I want to pick 1 red ball from the 3 I have, and I want to pick 1 white ball from the 1 I have, and I want to divide it by all the possibilities I have, which is 4 choose 2. So same sort of approach as I wrote the last one. Is that okay with everybody? And if you want to, you can just write down what it means. So this is choose 1 red from 3, choose 1 white from 1, and that's what the top 2 things mean. Trade on your calculator, what do you get?
Get half.
So someone reckons a half? Sounds good to me. You need to be able to get the answer yourself, of course. But not a bad thing, just pull your calculator and see, can I actually get that? What other ways of doing it? That's the combinations approach. We could try the direct approach, much like, which is the way you preferred it last time, so let's just try to do that sort of way. So to get 1 red and 1 white, well, let's just do what's the probability of 1 red first. So the first ball's red, then the second one is a white ball. That's one way of getting a red and a white. So you have the red first and the white. You could have the other way around, which we need to think about in a second. So if the first ball's red, what's the probability that the first ball is red?
3 4.
So you still got 3 red balls to pick from out of the 4 we have in the bag. We want to multiply because we want to have another AND event. And then we've got 1 white ball that we can pick, just one of them to pick from. And how many balls are left in the bag to pick from? 3. So it's going to be 1/3. So if you multiply those together, you get
1/4.
1/4. That's not the same as the previous answer, so something's not quite right here.
You need to account for choosing the white ball first, so you need to.
Okay. So the problem is, we would also need to do the other order. So you need to do the other order as well. Now, how can you handle that different order? One option is just to do it like I'm doing now, just do it directly. If you want the white one first, how many different ways of picking the white one first?
1/4.
So you've got 1 white ball from the 4 in the bag possible. Multiply by, after you've taken that 1 white out, you'll pick a red. So how many red balls are there to choose from?
That's 3.
So there's 3 of them out of 3,
So 1.
It'll just be 1/4 again.
which again is 1/4.
Add them together.
And if you add them together, that would give you the total number of ways of getting a red and a white,
Not even half.
which gives you a half. So that's the direct approach along the way. You could do both steps in the same way. So you're going, let's just, if I want to get 1 right and 1 red and 1 white, I can see that in one particular order, it's 1/4, probably 1/4. How many different ways are there of ordering them? Well, I've got 2 things. To order 2 things would be 2 factorial. So if I multiply the 1/4 by 2 factorial, it would give me the total probability, which gives you the half again. Now, for this case, there's only 2 orderings, not that hard to do, but that's a useful technique when you've got lots more orderings. So there's a number of ways of ordering that particular arrangement. One other approach, so we've got the combinations method, the direct method. Let's do complementary. So the probability of 1 red and 1 white. The complementary event is to think of the opposite event. And then the probability will be 1 minus the probability of the opposite. So what's the opposite of getting one red and one white? What's the opposite of that? So if you get two balls from it, pick two balls from this bag, one possibility is you get a red ball and a white ball. If you don't get that arrangement, what would you get instead?
2 red balls.
So you get 2 red balls.
But there is no second one.
Can you get 2 whites? No, because there's not enough whites to do that. So as a matter of fact, that is it. That's the answer.
To get white, you've got to get 2 reds.
Yeah.
Simple as that.
So the opposite in this case is just 2 reds. What's the probability of getting 2 reds? Well, we did that a second ago. That's what we did that before. And so it's equal to 1 minus the answer we had before, 1 minus a half. So the answer must be a half. Now that only works if the complement's easier to deal with. In this case, because we've already dealt with it. But sometimes that's a useful approach. So it's 3 different approaches here. So we had the combinations, we had the direct approach, and we had complementary event. Who preferred the combinations in this case? Okay. 4 maybe. Who liked the direct approach? 1 person by themselves. Maybe 2. And the complementary approach?
The
No, maybe
direct
3 people.
approach is,
So it's a bit, that one's more evenly spread out.
the direct approach is usually always easy to figure out. Like you can always break it down some way to find it. Whereas
So the problem with the direct approach, sometimes it might be really long.
yeah.
And that's what really gets in the way. The other indirect approaches sometimes are quicker. Certainly the complementary approach. Okay. Okay, this didn't quite copy. Let me finish the sentence off.
Is it on the next slide?
It is, but it's only 2 words, so I might just write it down. So when you're pulling 2 different names from a hat of 30 people, just the names, not the people themselves, the first name, what's the probability that the first name drawn out is me, and the second name drawn out is your friend, whatever it might be?
I didn't put mine.
130 times 129.
Okay, so you've got the direct approach, which seems reasonable in this case. The probability of me, then you, would be, well, I've only got 1 name, and there's 30 to pick from. And then I want to do the other way, so then my friend's only got 1 name out of
29.
the 29 left. So that's the direct approach. You can also use permutations, actually. So because we want to order, we have to do a permutation here. So the permutation approach would be, there is one ordering that I'm concerned with. So the one ordering that I want is me first and my friend second. So I've got 1 possible ordering I have in my mind. How many different possible ways are there of ordering 2 things from 30? How'd you work that out? That's more than what I'm going to know.
8. The P2 and
So it's 30 P2. That's right. So the number of ways of ordering 2 things from 30 would be 30 P2. And those 2 numbers are the same. If you type in your calculator, you've got the same. Yeah. Which is fortunate. So they both work. Which is easier? In this case, it really doesn't matter probably, and you'll get the answer quickly both ways. But it's good just to see there's more than one way of approaching it. Sometimes the permutation, if I wanted to pick not just 2 people from the hat, but 10, the latter approach using permutation starts getting a bit more appealing to me to work it out. Just because the calculator and how to simplify those things are easier. So this is slightly different. What's the probability, same pick and who from the hat, of getting you and me. So how is this different to the last question, I guess, is the first one?
This one's
It doesn't matter.
Okay, so we don't care about order. That's the only difference. So, any ideas what to do?
It's just going to be the same as last time because there's there's 1/30th chance of getting one of you and then 1/39th of the other.
But then you've got to do it again for the
No, you
opposite
don't.
way around.
No, you don't.
Yeah, we do, because you have two different orderings possible.
Yeah.
Where I'm drawn, then you're drawn.
Yep. So there's various options. One way is to have the same answer as before. So it's 1/30 times 29, but there are two orderings that we're concerned about, not just one anymore. So we either like you, so me then you, or you then me. Both of them are okay. So there's just twice what we had last time, is one way of looking at it. You can do it, because we don't care about order, we can also do it in terms of combinations. So the direct approach is like, and we did here, you have to consider both orders separately. Now you can either do that quite explicitly them separately, or like I've done here is number of orders we are happy with. So the combination approach would be, there's only one combination I'm interested in, you and me, it's the only combination I'm interested in, and divide by the total number of ways of choosing without order 2 things from 30. So how many ways are of choosing 2 things from 30?
435.
So it's, in general it's 30 choose 2, which is what the number you said, I think.
435.
435.
So it's 870/2.
Yeah, that's right. So you can do, and the combination automatically gets rid of the ordering for you, essentially. So the formula your calculator knows for it would automatically deal with that factor of 2 for you, essentially. So which approach do you like here? So who likes the first one? No one? I one first. Who likes the combinations? So most people were pretty non-committal about what they would like in that case. Does that mean you don't like anything?
They're both
Yeah.
pretty easy.
Especially, look at Paul's beard. Look at Paul's beard though. It's just irks me all day.
Just look at Paul in general. He's a disappointment to his class.
Oh my god, that's rude. It's just his,
That is pretty rude, I would cut that.
it's just his beard. Look at it. Like,
He looks like my kind of master.
That sounds like bullying to me, and it's being recorded, so you know.
You missed out, Paul.
5 on the 5.
Okay,
chat about it.
so they're just some examples of.
You missed out as soon as you go out with
Yeah, it's enough, guys. So they're just some examples of both independent and dependent. You can see for independent, you just multiply them out straight away. But even if it's dependent, you just have to work out what the probability is at each individual step. You just can't use the same probability over and over again. But if you're carefully about it, you can work out what it is. But instead of doing that direct approach, you can use the fact we know combinations and permutations to do lots of that in one go for you, if you're prepared to do it. You don't have to, as you can see, it's not required, but it's only a choice you have sometimes. So this is a case where it may not be immediately obvious. So you've got 2 different events. You've got picking kids, having kids in a family.
or money.
Money, is it? No. So you've got kids in a family, you've got 3 kids. One possible event is you've got, you have at least one boy and at least one girl, essentially. You've got boys and girls. And the second one is you've got at least one boy in the family. Are those 2 events independent? Does the outcome of one have an impact upon the other one?
No.
Well, F affects E.
Wow.
Yeah, because if you have both boys and girls, then you need to have at least one girl, whereas the last one, it can be 1 boy, 2 boys, or 3 boys.
So F kind of, you need to have F to have E.
So E affects F.
No, I say F affects E.
So if you got one direct, if you can say that F affects E, then it's true. Then vice versa is also true.
It's gone. Yeah.
So if you can see a dependency one direction, it automatically implies dependency the opposite direction. How these things work, they're symmetrical. It might be a different sort of dependency if you look at it that way. So the consensus is?
Well, one of the options of F means that E can't be possible, so they are dependent.
So it seems like they are dependent. Now, are you convinced from intuition, which is what people are arguing for the moment?
No. No.
If not, then you can just actually list them all out. And it isn't bad at first look.
So yeah, they are dependent. There you go.
They are dependent. And the reason is, as people said, if you've got at least one, if you've got both boys and girls, then you have to have at least one boy. So if E is true, then F is automatically true. So the outcome of E does have an impact upon F. Sort of thing. That's a dependency you can see. But you can just list them all out, so you can go, well, E and F, there's not too many choices for 3 kids. So there are 8 options, essentially. List them all out. How many of them satisfy E? Well, most of them do. So anything but all boys or all girls. So it's 6 out of 8 work. F, to at least one boy. You can't have all girls. That's any problem. That's anything you don't want to have, I guess. That's probability of 7 out of 8. And so the formal definition of independence really is the probability of E and F is equal to the product of probability of E times probability of F. That's the formal definition. You can actually check it out in this case. You can work the other two out. So probability of E and F together is just 6/8. The product is 21 over 32, which doesn't simplify. You can see they're not the same number. So you can prove mathematically they're not independent if that's what you want to do that. Most of the time with independence, you can normally just see it more from an intuitive point of view. Go, I can see there's a dependency there. If you're choosing a bit more obscure events like these ones are not quite so direct, it's sometimes hard to see that, and having a backup way of proving or otherwise is useful. But most examples you all want to consider, if you thought now about the English definition of independence, you probably can work it out. But it's nice to have a backup, I reckon. So, the two special cases we considered are mutually exclusive and independent. So can something be both special cases at the same time? So can two events be both mutually exclusive, which means they can't have at the same time, and can they be independent? The outcome of one doesn't have an impact upon the other.
Yes.
Okay, if you reckon yes, give me an example.
Shit. Jacob can sneeze and I can go outside and shoot David. But does that mean
That works.
they don't have it in the same room?
Yeah, but does that mean that...
Are they independent of each other?
Yeah.
Well, me sneezing doesn't affect them having some form of gun battle out.
It's not even a gun battle, he's just lining me up.
Well, assassination then. Or
Very much.
like,
You know, Corey, if you're going to do it in the exam room. Everyone will pass.
Oh, I like your thinking.
No, we'll get a supplementary exams.
They had to witness a murder in cold blood, but you still have to do the exam.
You get to have another go at it.
So has it actually happened before? Does that mean?
maybe he's talking from experience.
No, I've never known of a murder happening in an exam centre. And I hope I never hear of one too. So the answer is not really, but I'll explain a bit more carefully. Remember that.
The war, yeah, you use your supplementary
Come up with a reason for it.
Now,
Tremors.
I'll do it mathematically first, and I'll try to explain it intuitively. So what does mutually exclusive mean? Mutually exclusive, the definition is the probability of two events happening is equal to what? 0. That's what mutually exclusive really means. They can't happen at the same time. If they're independent, so two events are independent, what does that tell you mathematically? The probability E and F is equal to what?
Is equal to E or F.
So if
E given
that,
F or F given E.
And
no, essentially.
PE times PA.
Hmm?
PE times PA.
So it's really, so if you've got the probability of E and F, it's just the probability of E times by the probability of F. That's sort of a definition, mathematical definition of independence. That's what it satisfies by. So the first one's by mutual exclusivity, the second one's by independence. Therefore, those two things must be equal if both of them happen at the same time. How does that happen?
When two things are impossible.
Okay. So PE times by P of F must be equal to 0. When does that happen?
Both of them have 0. Well, one of them has 0.
It means that at least one of the events has a probability of 0. So let's say P of E is 0 or P of F is 0. What does that mean? Which I think you've said it already effectively. It means it can't happen. So the only way of getting two events to be both mutually exclusive and independent is if one of them can never happen at all. Which is why not really is the answer. So yes, in a trivial sense, perhaps.
Yeah.
So does that match your situation?
Yeah, I don't have a gun. It can't happen.
But you could get a gun.
So why does that work? So if things are mutually exclusive, if one thing happens, that automatically makes the other one not being able to happen anymore. That's a dependency. So the only time that independency doesn't get in the way of independence is if one of them was never going to happen at every time, ever at all. That's the only time you can get around it. But if mutually exclusive, if one happens, the other one can't happen, that creates the dependency normally. So apart from a non-trivial example, things can't be both special cases at the same time. That's okay, you normally just do one at a time. Can something be neither of the special cases?
Yes. They cannot happen at the same time, they're independent.
Well, if you jump off a building, right, halfway through freefall, you take the parachute off.
Okay, let's do show of hands. Who reckons yes? Their hands aren't very showing high. Who reckons no?
Oh, it's very different.
So that means that they are mutually
That means they can happen at the same time
and they're dependent.
and they're dependent upon each other. Okay.
Yeah.
So yes.
Yes.
Can you give me an example then?
Us both having candy and me giving you candy so that you have some.
That's one there. I can see a lot of the examples in these slides are that.
It's just so strange example.
What?
I don't know.
That one there is an example. So E and F, those two things can happen at the same time. So they can happen at the same time 6 out of 8. So 3/4 of the time they happen at the same time. But we've already worked out they're dependent upon each other. So they're dependent and not mutually exclusive. And so, as a matter of fact, most things are probably neither. I mean, that's the common scenario. But we would often like to try to manufacture things to get these special cases happening where we can to make the formulas easier. In particular, mutually exclusive, you can control that one much easier. But therefore, when you're trying to control stuff, it's good to try to make them independent. So, as an example, if you're trying to design a new interface for your web app. One option is to have two different designs. And when someone logs into your web page, you just randomly assign them one web design or the other.
That would
Horrible.
get very, very
That sounds
annoying.
really
It's
fun.
Terribly,
Is Google
unintuitive.
listening? Google, you know, be listening.
Okay, so the last time I've seen that happening is PayPal. So I've seen them do that.
And it still happens sometimes when you log in, you get the old version, and sometimes you get the new version of their web interface.
Presumably the reason why they do that, it really is user interface testing.
I want to mix them all.
They would like to see, they would then see how many, for each different page, they'll see how many they click through to get the sales or whatever it might be, or whatever their key performance indicator is. And therefore they're going to use it to evaluate which page is better than the other one. So it's called A/B testing. And so if you want to do that, in order to get everything, to make the formulas easy to analyse afterwards, you really need to make sure things are independent from each other. So it really should be a genuine random assignment between whenever someone comes, rather than, let's just today's Monday, let's just put all the old interface up for Monday. Tuesday, I'll put all the new one up.
Well, I've seen that done is when you go on, you get assigned a permanent interface so you don't change, but someone else isn't guaranteed to have the same one as you are. Because if you as a user continuously have it changing on you, you're just going to chuck the shits and give up trying to use it. Yeah. You know.
So the intention is you shouldn't normally notice it. So the reason why you're noticing it, well, I noticed it because I was trying to test something else for some other web page, and so just refreshing a page often what a normal user wouldn't normally do, and that's how you can pick it up. So you're right. If they're doing it properly, the single user, if they're doing it using the system appropriately, should always see the same set of screens.
Yeah. That's why they assign a cookie. It's like you get that cookie in that interface.
Yeah.
It depends how many screens they'd have to show you, etc. as well. So PayPal, most of the screens are supposed to be in the vendor site, not theirs. So they can get away with doing it differently. But you can see, so that sort of idea of, so it's business analysis. It's important to understand probability, and independence really is helpful in that circumstance. It does make things. And you can control independence by how you assign the different pages to different people. So you can control that. Sometimes, like picking balls from a hat, you can't control independence. It's just, it is or it isn't, essentially. Okay, so this is the example that motivated probability. So there was this guy who liked gambling, and one of the games he liked gambling, this is the question he actually asked, is if I roll 2 dice 24 times, what's the probability of getting at least one double-sided 6? Why he asked that is because if there was a double 6, he got double his money back. If there wasn't a double 6, he lost his money. Essentially, that was the game he was playing. And he wanted to know, was it worthwhile playing the game or not?
Yeah. He did no outcome.
No, it's not a low probability.
No, it's pretty good. Probably, yeah. I'd do it.
And so he asked his friend Fermat what the answer was, essentially.
Played enough dice.
So Fermat is known more famously perhaps for his last theorem, which is the... Have we heard of that before? So Fermat's last theorem...
The last theorem. It sounds like a movie. Leonardo DiCaprio, Denzel Washington, in a race against time to secure the last theorem.
Okay, so that Fermat's last theorem, I won't write the whole thing down, but that for any integer, there are non-trivial solutions to that equation. So you know so you got Pythagoras' theorem. It's one of those cases, n equals 2. But is it true? Is it possible for other n values? And he wrote it, and Fermat did lots of maths, including the one on the slide. He just wrote in the margin this little theorem, and he said, "Oh yeah, it's easy to prove. I just don't have quite the room to prove it right here."
He's had a heart attack right there. He had a heart attack on the spot. That was his last theorem.
Oh no! And so it's his last theorem because he wrote lots of results down like that. Some of them he proved, some he didn't. And people have gone back reading through his writings and proved lots of things in. But this one always was the one that no one could work out how to really do. So when he wrote down, I can see how to prove it, he probably was wrong. He probably couldn't see it because it's quite difficult. And so it has been proved now, more recently. It's the last one proved.
Didn't it take I think I was reading something that took like 400 pages of something just for some guy to get it. And then he got it wrong. He realised he got it wrong. And then he spent the next year fixing his mistake.
So no, how research often works is based on funding, right? So money is always the big deal. And so most of the time people get funded for a short period of time. That's what normally happens.
You got to try and convince someone to give you money.
Oh no, it's part of my job is to do research. So therefore, and lots of the other lecturers, they do research on various stuff. Some of them are applied, some are a bit more theoretical, like this result would be rather theoretical, which you can appreciate. But the answer to this is all about elliptical integrals. Like they produce a lot of other mathematics to try to justify it, which do have benefits. So that looks like why hair actually it's important.
The book.
There's lots of different research is important.
It's pretty big.
And so this guy managed to persuade people to fund him for a few years just so he could look at this problem just to look by itself, which is very abnormal for research in general. But anyway, so Fermat, one of his other thing he did was define probability, so he introduced it, and this was the first problem that motivated it. Let's see if we can answer the question. So the answer is, if the odds for the game are offered a 1-to-1, so if you play and if you win, you get double your money, should you play the game or not? Essentially is the guy's question. So probability of at least one double six.
So 24, 36, wouldn't it?
How would you do it?
Find out the probability of getting 166.
Okay, so it's at least means greater or equal to 1, right? So at least 1 means greater or equal to 1. So if you think about the direct approach would be 1 or 2 or 3 or all the way up to 24. There's lots of choices. I don't really want to work out all those choices. So an easy approach then would be to do the opposite. This is definitely a good example to do the opposite for it. What's the opposite of at least 1?
No, double sixes.
Yeah. So you're tossing it 24 times. Are each dice roll independent or not?
Yes.
Yes.
So they are independent. So that helps, right? So the fact they're independent will make the form much easier. So basically, we work out the probability of no double six for the first roll, and it'll be true for the second roll and the third roll and the fourth roll. So it'd be some number, which we'll work out in a second, for all 24 times. So just that to the power of 24. And that's because they're independent. I can write that down so easily. What's probably the first dice roll is not a double six?
5, 6.
So there's 2 dice, so it'd be 36.
5, 6. 506 times 506, so it'd be like 25 over 36.
93.
So you can do it different ways. You can do, right, as you say, 35 over 36.
Was it 25 over 36?
No, because the chance of getting 2 double sixes is 1/6 times 1/6.
Yeah, sorry.
So it's easier.
Thought I heard you 37.
So it's easier to write it in this way, I reckon. That is, you don't want a double six. So how do you get a double six? Well, you want a 6 and a 6. That's 1 and a 6 times 1/6. We did that before. It's 1 over 36.
Yeah.
And we want the opposite of that. So 1 minus that would be 35 over 36. So this bit. So the number of ways of not getting a double six on just the first roll would be 35 over 36. So most of the time. But we got 24 different times of doing it. So playing this game many times. So it'd be that number to the power of 24. If you type all that in your calculator, and remember when Fermat did this, I try and work, this is a few hundred years ago when you worked this stuff out, he wouldn't have had a calculator.
It's like 49.1% or something.
49.1%. Someone reckons? We'll do it democratically, see what else someone else can get the same answer or a different one.
I'll look through. Yeah, same.
Did you do the 1 minus? I mean, that's my question.
Yeah, 1 minus 35 over 36 to the power of 24 is 0.4914038761.
What's the answer? I thought the answer was 50 points something or other. So. But I might be remembering. That's my memory, which is not as good as it used to be.
Yeah,
Well, obviously, you can take wrong.
Well, 35 over 36 to the power of 24 is 0.5085961239. And then 1 minus that is the...
Yep. Okay. Cheers. Thank you. I just remembered it incorrectly then.
Usually it works.
So, would you play the game?
No, that's not good. Mine.
So, would you play the game for the odds of
it's 1.
1 to 1?
2-up's pretty fun, so...
If you play the game over and over and over again, then with that sort of odds, that means you eventually lose your money. If you had a lot of money to begin with, and you could afford to play lots of games. It's less than 50% chance. So an odds of 1-to-1, basically, if you get playing a lot of time, if the true probability was 50%, then you make no money on the long run. If the probability is greater than 50%, it means you could actually make some profit out of it if you're stuck in long enough. And you had a lot of money in your disposal just to ride through the losses, so to speak. So the fact it's less than 50% just means it's slightly not fair. Now that's much better than what you get in a casino, I might add.
Like slightly not fair. Oh man.
Casinos operate because they're trying to make profit, right? So you would never get such a good deal from a casino. But this is the day before people knew how to work out odds correctly, essentially. They didn't really have a good concept for it. And so people observed that this seemed okay, but Fermat did his calculations and said, oh no, here's what the real probability is.
I can see a common mistake might be if you worked out the probability of getting 2 double sixes, like 1 over 36, and you just multiply that by 24, thinking, you just do it 24 times, because that's very much so in your favour, but
yes.
So that's 2/3 then.
And so there's common fallacies of probability, which I presume might have exhibited back then. And most people know the words likely and probably mean in some sense. So probability is commonly understood, only in broad terms. People have to make mistakes in the details.
So in terms of gambling, this guy screwed everyone over.
He made a lot of money, and he was already rich from other things. I don't know what he was, but I think he made money from gambling. Yes.
No,
more money
he
off
made
gambling.
But he was but for Matt wrote to another friend about him, and he said he's not a mathematician. No. He's an okay bloke, but he's not a good mathematician. He would have written French in Italy rather than. All right, let's have a break for 5 minutes.
He was like Voltaire, and he just bought all of the lottery tickets because it costs less to buy all of the lottery tickets than the winnings. So if you bought all the lottery tickets, you win more than you lose from buying them.
I think that's true.
It's true.
Officially less.
That's how he did it.
The
1700s in France.
That's true occasionally in Lotto in Australia, but where they're trying to remember which one it is. It's the one with a cat in the ad. So the Lotto went high enough that the expected value was positive for a change. Well, the expected return is negative for Lotto. But the problem with Lotto is that more than one person could win it. So even if you did buy all the tickets and guarantee you win that way, you might share the prize with someone else.
But we bought all of them, so no one else can buy any tickets.
Yes.
Yeah, but therefore you share a prize pool with yourself.
But basically what you do is you buy a ticket for every single number, but it doesn't stop other people buying tickets for the same numbers as you do.
You buy their tickets off we buy all of the tickets.
So the problem with Lotto is, although very occasionally, the jackpot gets high enough to consider that sort of option, if you did lay out a lot of money to buy all the possible numbers I should say, then you never guarantee that someone else doesn't share the prize with you.
I know there was one that was like something like 100 million or something, and everyone, like there was a lot of winners, and each person who won only got like $6,000 or something. It was tiny.
Yeah. Oh, they don't. Yeah. So normally they don't get that bad. But the other thing is, Lotto still is not a good investment. Essentially, even when the jackpot was really really big, probably still even then it's probably not a good investment.
The odds of winning is just astronomically low anyway. So.
See, no point.
But if you're doing Lotto to try to make money, don't do it. If you try to do it for other reasons, like you think it's fun or something like that,
Or it's an addiction.
If it's an addiction, then that's not a thing. That's not a good reason.
A gift. There you go.
What are you talking about?
The only reason I know people buy lottos these days is a gift for someone.
No, then you buy a scratchy.
It's a gift for me. Treat
Well, a
yourself.
lotto or a gift, like a scratchy, the only reason I actually know people buy them.
And then when they win, you get half.
So if you do gambling, you have to be
It doesn't
prepared
work
to
like
lose.
that. I'm greedy.
What?
If you give me a scratchy, it's all mine. Piss off.
Damn it!
3 more minutes. So you can actually walk around if you wish, guys, or check your emails or text messages. That's okay. Yeah, that's fine too. You can get afternoon tea.
What he did, right? Because I wanted to buy lottery tickets to the value of their power. You like all the lottery tickets. It's hilarious.
Go on by them next morning. I think so many paychecks go through.
Split bubbles and bonds.
Quick. Roll the dice. What's this day tomorrow? How exciting is that?
Oh, I'm not excited at all. One thing online.
You don't have to do it online, you can fill it on a piece of paper, mail it in. Census Day.
Census Day.
You can do it at midnight. No, we expected you.
Oh, cool.
Some of the way.
That was another one.
Oh, really? Oscar's just getting old. Oscar's just really.
Which is
Optical illusion.
you expect that that's what's going to happen, so you rent the space accordingly. That wouldn't be that hard to get.
Yeah.
25.
Optical illusion.
You just lost the perspective of
Alright. We'll do one more extended example on this, and then I'll look at the question 3 and assignment 1 for people who did or did not get it. So regrettably it's easy to pick on gambling as an examples for probability. So this is another one, poker. But you see probability in lots of different games, and poker's an example, but you see it in Monopoly, and is indeed most games. You see some sort of chance in there. And understanding those is important if you want to design the games. This is an example looking at 5-handed poker. 5-card poker, where you've got each hand, it has 5 cards in it. So just clarifying, just in case you don't know cards, so it's 52 cards in the deck, 4 different suits, and each suit's made up of 13 different numbers. So ace, 2, 3, up to 10, jack, queen, king, in case you don't know. So that's the standard poker. What happens if you're still dealing 5 hands, 5 cards to everybody, you deal 7 cards to everybody, and they can pick their best 5 to make a hand? How does that change the game? You deal 8 and they get to choose 5 from it. How does it change the game? And those sort of things you might want to consider from a design point of view, to go like, some of those arrangements can make it so much easier to get the higher end stuff and make people feel good about themselves because they get another really good hands. But how much does it change the game dynamic? Understanding probability of those things would be useful for that sort of thing.
Isn't that almost like Isn't that almost like
Yeah, that's what some of them do. That's right. So when they modify these rules, and they do it for poker as an example, people modify the rules a lot. But how does that? If you understand the probabilities, how does that really change in the game or not? And understanding those differences is important if we're going to play it too. So let's just do some. I haven't picked them all out here. I didn't like it. Okay, so let's work out the probability of getting various things happening. So the first one we'll do is 4 of a kind. Now, Does everyone know what I mean by 4 of a kind?
That's when you get 4 of a kind. What's the probability of getting 5 of a kind? That's a tough one.
Okay. Can someone tell me what the probability of getting 5 of a kind is?
There's one way.
0.
0.
What? I've got it once and they kicked me out.
Okay, so in order to do probabilities, you need to know the number of ways of getting this particular thing happening divided by the total number of ways of it happening. That's sort of the basic idea. So what's the number of ways of picking 5 cards from 52? I mean, that's basically that's what poker is really about. How many different ways are there of doing that particular thing? I'm going to pick 5 cards from 52. Now it's going to be a combination or permutation. It's one of those two. Do we have order or not? That's really what it comes down to. So it's 52 something 5. Is it C for choosing without order or P for choosing with order?
C.
So you don't care about the order because when you get the cards, you can move them around any way you want to choose the order you feel see fit. So order doesn't make a difference. That's why it's a combination, not a permutation. So when you're picking things, it's really just thinking about order as the key idea.
How many different ways to pick 5 cards? 5 of a kind. Ooh. I can do 5 of a kind, like, wait.
So let's type some of these things up in Excel just so we can see the differences. Never. Good time to optimate. So we've got combination. I do want 52 choose 5. So that's the number of ways of picking 5 cards from 52.
That's the right number.
Okay, so we want to do various options.
No, you should permutation of it.
So we want 4 of a kind. That's the first one we want to do. How many different ways are there of getting 4 of a kind? So 4 of a kind would be getting, right, something like ace, 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 and another card. 10, for example. So it's 4 cards with exactly the same number, different suits, and the last one would be anything you want to at all, really.
Same suit.
So the 4 aces, incidentally, in that case, would have to be with the 4 different suits for it to make sense, unless you're cheating still. So that's what I mean by 4.
Never lost a fair game.
So the probability then would be the number of ways of doing that divided by 52 choose 5. That's what the probability is going to be. So we just have to work out the number of ways of getting the 4 of the kind. Ideas.
14, 15.
So the first thing I would do is let's pick the number which is going to be the 4 of the kind. How many different choices do I have? So you've written an ace here. So how many different ways of choosing ace or something like that?
We got 4 out of 52 for the first ace because there's.
No, mate, it's just a whole block of numbers there. It's a whole block of 4 numbers that are the same card. So how many different types of cards do you have? 13. So you've really got 13 choices to choose what the 4 kind would be. Once you've chosen ace, you automatically get all 4 cards for free. So if you want to think of that way.
Okay.
So you've got 13, and you get the next 3 cards would be times 1, times 1, times 1. If you want to put it explicitly, I'm not going to. So the only other card you have to worry about, that picks those block of 4. The next thing you have to worry about is picking the last number, the last card. How many choices are there for the last card to make it up?
Doesn't matter, so it's me.
So it's 52 minus something or other, that's right. So we've got to make sure that the last card you pick hasn't already been picked, essentially. So how many cards are already picked?
4 cards.
4.
But you can't pick another ace.
So you can't pick another ace, essentially, because we've already worked out 5 aces is cheating. And so that will be the answer.
That's 5. You're just really good. You're really good at poker.
So putting that down, so we've got 13 ways. I'll just type it in here. So, 13 ways of picking what number is 4 of a kind, and multiplied by the 52 minus 4 ways of picking the last card. There's only 624 ways of getting that. So hands. And so the probability would be that divided by this big number. That would be the probability. Doesn't happen very often.
Pretty good odds.
So you multiply that by 100.
You got,
That's the percentage. So it's a 0.024%. Very, very unlikely. Let's put a little coding in here. So it's number of ways, probability, that's percentage. So let's do other ones. We'll do a full house. So full house means you're getting 3 of a kind for 1 card
Jokes on you.
and a pair.
and a pair. So 2 3s, for example. So 3 of a kind and a pair essentially is what makes a full house. So how many different ways are there of doing that particular one? So again, the probability would be divided by the same thing at the bottom. So it's the same every single time. How many ways of getting a full house? So first of all, you have to pick what you want for the 3 of a kind part. How many choices do you have for the 3 of a kind?
13.
13. Now, unlike the 4 of a kind, I'm going to pick only 3 cards. I'm not going to pick all 4. So I've got to pick 3 different suits I want. How many suits are possible? 4. So of the 4 suits I have, I want to choose 3 of them. Does that make sense?
Yep.
So I've got to pick 30. Got 13 now for options what the 3 of a kind can be. Once I worked out what it is, so ace, my example, I've got to pick 3 suits of the 4 to work out what it's going to be. What about for the pair? How many choices do I have for what the number of the pair is going to be?
12.
Okay, so why not 13?
Because you've already done a number for the 3 of a kind.
Okay, so we've already picked something for the 3 of a kind, so we have to do something. We can't choose that one again, so then 12 other choices to pick. So 12 other choices of what the pair is going to be, and then I have to choose what suit it's going to be, what suits they are.
4 choose 2.
Yep. So times by 4 choose 2.
Get the full house hand, then the fuller house.
So it's 13 times by 4 choose 3 times by 12 times by 4 choose 2. So that's more likely to get a full house. And just copy everything across. The probability is 0.1%, 1.5. So again, not very likely.
But a hell of a lot more likely than 4 of a kind.
Yes. That's being dealt, and this is the probability of being dealt with immediately. So in real, so if you get to shed some cards and be dealt new ones, the probability goes up a bit. So what other ones? What about 2 pair? So 2 pair means you're getting 2 numbers are the same, another 2 numbers are the same. They're not 4 of a kind. We want to exclude 4 of a kind explicitly, and you get something else to make up the numbers. So 5 at the end is an example of a 2 pair. Okay, so ideas. We probably get it wrong the first time round. We'll have to fix it up. Well, let's see how you guys go.
13 times 4 choose 2.
So 2 pair, does that rely on us only getting 2 pairs? Like,
We want to exclude the option of 4 of a kind.
isn't a full house still You know, 2 pair and also 4 of a kind.
Okay, so we want to so for 2 pair, we explicitly would like to exclude full houses and 4s of a kind. That's your question, I presume.
Well then, yeah. So
Yep.
shouldn't it be 1 minus the probability of those 2 put together?
Oh no, we can set the way you set it up, you can just exclude those cases out if you wanted to. So we'll try that out. So if you want 2 pair, we have to pick what number is going to be in the first pair. Essentially, is the naive approach. Oh, we can make it better in a second. So how many options are there for the first one?
13.
So 13, and we're going to pick what suits are possible.
4 choose 2.
So 4, choose 2. Then what do we do next?
The next pair.
Which would be
12 times 4 choose 2.
And what do we do next?
So it'd be... So it'd be 52 minus 8, yeah.
Yeah. So we've got to pick the last card, and the last card can't be any of the other letters already picked. So minus 8. That's incorrect, unfortunately. Although that seems to be the right answer. What's wrong about it?
Isn't it once again because you can double up on the something?
So again?
Because you can double up on the pairs.
So if you do that sort of thing would count AA335, and also count 33AA5. It would count both of those as a separate entity. But if you look at them, they're the same.
Overlap, yeah.
So it's counting it's counting everything twice.
So just divide by 2.
So if you divide by 2, then it's all sweet. How can you do that automatically? So one option is to divide by 2. The cleaner approach is to say, I would like to, out of my 13 different numbers, I would like to choose 2 of them to be the 2 pair. And then it does it automatically for you. Now you could just divide the other one by 2, that also works. But you really got to go, I've got 13 different numbers, I would like to pick 2 of them to form each of the 2 pairs. And it does that automatically for you. That one's trickier, it certainly is. So let's try to, this is the 2 pair. So I've got the 13 choose 2 for the 2 things are going to be the 2 pairs, multiplied by the 4 choose 2 ways of getting the suits for the first pair, times by 4 choose 2 for the second pair, and multiplied by 52 minus 8 to pick up the last number. And so you can see the numbers getting bigger. So these are more common. And so the probability of getting 2 pair is almost 5%. So if you play 20 games, you'd expect one of those games to have a double pair, 2 pair on being dealt with it immediately.
Oh wow, my luck. That's a lot of money to lose. 2 pair always wins.
Sorry.
2 pair always wins.
Always.
Always. 100%. What if the dealer gets 5 of a kind? Because the dealer always wins.
So 2 pair is starting to get it more common. Would you call that common though?
Oh.
No, not really.
Oh, something stupid. I don't know about you, but when I hit the dealer with that draw 4,
You're going to be like when I hit the dealer.
I don't know, man. When I hit the dealer, he does. What's the probability?
Okay, let's do 1 pair. So we still have to divide by the 52 choose 5. We've still got to work out the number of ways of getting 1 pair. And 1 pair would be a pair and then some other numbers. 3 other different numbers, essentially. That's what we're looking for. So we won't exclude full houses, 4 of kinds, 3 of kinds, 2 pairs. Just want to exclude all those cases. Just a pair, nothing else. How many different ways are there of doing that? Okay, so you've got a. So for the pair, you have to pick the two suits which make up that pair. So 4 choose 2 for picking the suits for the pair, definitely. What does you have to do?
You'd have 13 different options which
Yep.
pair to choose.
So 13 options for pair to choose. Yep. So that's basically gets the pair sorted. So now we have to worry about all the other numbers.
And then it'd be like 52 minus 4 choose 3, wouldn't it?
52 minus 2.
So it's 52 minus 4.
Because you.
But you don't want to have. Say, but,
that.
yeah, go on.
So you're excluding that pair, like that
Number.
that number, yeah.
So if you pick the pair to be 2 2s,
Otherwise,
you don't want to have any more 2s cropping up.
Otherwise, it's 2 pair.
So you got 52 minus 4, so you got 48 other cards to worry about, and how many of those do you want to pick?
3. So choose 3.
So you want to choose 3 of those to make up the rest of the number. You don't care about the order. Yeah, is that right?
Yeah.
Probably not.
Well, damn, as you ask, it's probably not.
So the answer is no, it's not right. Why is it not right?
Because you asked.
Because there's some reason that we can't pick up on at the moment.
The reason, knowing the answer's not right, often it goes, oh, that's right, I can see it. Just being told that there's a possibility to look for. The reason why that doesn't work is because you might be picking 3 3s, for example, and it'd be a full house.
Yeah.
We don't want that. We want just the 2 pair.
You're like, damn, got the full house again.
Now, they don't happen very often, so I may not change the numbers terribly much, but so basically, we've got 12 other numbers, and we want to pick 3 of the rest of the numbers to make up the set. Make sense? So that will give me the 3, 6, and 9. Now, it's still not right, because I have to work out the suits. How many possibilities are there suits for, say, the 3 in this, as I've written the example here? 4. How many choices do I have for the suits for the 6?
4.
And 9?
Maybe 4.
Sorry, so it's going to be 4 cubed for all the choices of suits.
Which is 64.
And so this setup means I exclude things like full houses and fours of a kind, 2 pair, that sort of idea. We were excluding 4 of a kinds already, admittedly, but this excludes the full houses and the 2 pairs. So this is the pair. So 4 choose 2 for the choice, that's the suits for the pair, times by the number of possible pairs, times by choosing the numbers to make up the rest of it, and times by the choices for the suits for the rest of the numbers. So the probability of getting a single pair just being dealt with straight away is 42%.
Almost the original life.
So getting a pair is at least happens. If you play 3 games, you should get at least 1 on average. So you get at least 1 on average. What about other things? You have flush. Let's not make it too complicated. So what does a flush mean?
All the same suit.
So it means all the same suit. Let's avoid complications. Let's make it flush or straight flush or a royal flush. Let's put all the flushes together. So we don't have to worry about that sort of stuff.
Then there's the toilet flush.
So what's probably getting a flush? So again, it's over 52 choose 5. So that means they all of it have to be the same suit. Otherwise, we don't care about the numbers otherwise at all, essentially.
Unless it's a straight flush. Unless it's a straight flush.
Yeah, so let's count straight flushes and real flushes at the same time. We don't care about the ordering. So in real poker, yes, they're more special.
Good English? Good English?
You get a real flush and 5 of a kind at the same time. It's like instant win.
So how many? So you got to pick how many different flushes can you have? How would you think about it?
A lot.
So you got to pick the suit. So there's 4 different suits to pick from. So 4 choices for the suit. Now you got to pick the numbers. How many different? What numbers would you pick?
How many numbers? 5.
So you got 13 different numbers to pick from.
Choose 5.
And you want to pick 5 of them. They all got to be the same suit, so the ball will do the suit part for you. So 4. So 13, choose 5. So that's all flushes. So in reality, straight flushes and royal flushes are considered more special, and so they're sort of taken out. There's not very many of those though.
Doesn't a flush beat a full house? Doesn't a flush beat a full house?
No, it doesn't. No, it doesn't.
No, one of the kind beats everything.
So flushes between a 3 of a kind and a
Rare, it never happens.
That's why it beats everything.
full house, isn't it?
Straight flush, full house.
Yeah.
Okay.
3 of a kind's below a straight. It's a straight, got a flush.
Kind of horrible.
I haven't played for a while, you can believe them.
And then an Exodia.
So there's other options. I haven't done all. Let's just do the last one. Nothing. So that means you get nothing special. So no straights, no flushes, no pairs, let alone through. How many ways of doing that?
There's like a billion.
You just like you tell them to copy that.
The percentage change is 100.
Pick 5 blank cards.
So I want to pick.
Just go through. You just look.
So I want to pick 5 cards from the 13.
My cards are gone.
Now I've got to pick the numbers. Now, being a little annoying here, I don't want to. I want to have nothing. That means I really don't want to have straights as well. So you don't know what a straight is.
Yeah,
Isn't that like
1, 2, 3, 4, 5.
5? Yeah.
I mean, the cards have to be in order.
Concurrent.
In order.
And so, because if the bottom number has to be an ace or a 2 or a 3. So if you think about it, there's only how many different ways can you get how many different ways can you get a straight?
13.
Well, it's not going to be 13 because it's got to end in the top number. So
13 to be 5.
So the straights can either start with an ace, 2, 3, 4. You have an ace high at the top.
9.
Are you downloading Zinco Poker there? I think we started an addiction.
So
No idea what
you have ace, 2, 3, 4, 5. The high, that's one straight. The highest you can get would be ending an ace high, isn't it?
Yeah.
So you've got 14.
So therefore, they're all the possible straights. So they can either start with 1 or up to 10. So there's 10 different possible straights you can have. I want to exclude those 10 options. So I've got to have the minus 10 just to get rid of the straights. And then I want to multiply that by the number of ways to pick in the suits. So I've got 5 different cards. I pick the suit for each of them. How many different choices are for the suits for each card?
4.
4.
4 choose 1 suit.
So I've got to do. I'm going to. It's 4 choose 1 if you think that way. So I've got to pick a suit. 4 choose 1. I'm going to do it 5 times. So it's 4 to the power of 5. But I want to exclude the cases where I get flushes. So a flush would be they're all the same. There's 4 different possible flushes, are there? 1 for each suit. So the minus 10 excludes the straights, the minus 4 excludes the flushes. Otherwise, everything else gets sorted. So that's a harder one because you have to think quite carefully about all the negative circumstances. And so this is equal to, or I say, choose the 5 cards minus the straights. Choose the suits minus the flushes.
I like the nods.
And so you've got a slightly better than even chance of getting nothing being dealt to you.
Here are your cards. Where'd they go? I want more cards, please. These cards are rubbish. No. Oh.
So if you add up all those things, you only get 97.5%. Where's the rest of it? Why is why not 100% here?
They're royal flush.
So now we have royal flush is under. I put under here just to make it easier. So I've missed 3 of a kind.
Straights go.
And I've missed straights. So they make up the numbers. But you can work those out separately if you wish.
Well, you only have to work out one, and then you minus that from the other option.
No, I also haven't worked out straight flushes or
What are the odds that everyone gets a royal flush?
There's 4 people playing, and everyone gets a royal flush.
So what's the chances of that?
Wasn't a royal flush like one?
Very unlikely.
Never happened
Wasn't
in
a
the history
royal
of the
flush
game.
like
But
1
it
in
can.
4,000? Something like that?
Oh, it's so I will do royal flush if you ask for it.
There's 5 people
How many different ways can you get a royal flush? So royal flush means the numbers are ace, king, queen, jack, 10. That's what the numbers have to be for a royal flush. Have to be that.
They all have this.
And have to be the same suit. So how many choices do you have for the suit? Just 4.
There's 4 options.
So there's just 4 choices, that's it. And you can see it's having trouble writing it down. Yeah, so does anyone know what does that notation mean? The what is E minus 6 there?
Scientific notation.
Scientific notation? Yep.
So it's 1.59, so 53908 times 10 to the minus 6.
Yeah, so it just means 10 times 10 to the power
That's
of
so tiny.
10. Sorry, times by 10 to the power of something. So it's just their scientific notation.
There's 5 people playing. What are the odds of all of them getting a royal flush?
As well.
0.
As well as a 5 and a kind.
If we're using yours,
As well as 5 of a kind.
The royalist flush.
And a drawful.
Wait, what?
You know, you
What
play.
game are you playing?
reverse your turn.
Okay, so it's the tricky bit of working the probability of getting 4 royal flushes in being dealt straight away.
Wouldn't that be amazing?
So why it's a little difficult to work that out is because you've got there's all the different possible ordering, so it's more than your first thing. Because you can have the first person get clubs, or the second person have clubs, etc. So there's a few more options than at first glance, but still, it's exceptionally remote. So it probably means you haven't sorted the deck out properly before you tilt. So it would normally mean.
Or you should just go and buy a lottery ticket.
Okay.
That or you cheated.
Always going with the cheap card real quick.
It's you.
So that's so what I'll do tomorrow is to look at probability distributions. So what I've really done there, use Excel. I've done it incomplete. What I've done is worked out what's called a probability distribution for poker, essentially. So these are my options, just here, and for each option I've worked out what the corresponding probability is for it. That's called a probability distribution. And so I want to talk about more of those tomorrow, essentially. And knowing the full distribution, I haven't quite worked the full thing out here, allows you to do lots of things, like work out so if we then start placing how much money you win for each of these, then you can work out what your expected winnings are, etc. And the answer is probably not enough to worth doing it, but anyway. But you can work out expected value and you look at variability and things like that. So having a distribution, you can do more things with it. We'll talk more about it tomorrow. What I want to do just to finish up is just look at the last question in assignment. So this is the weakest question. I'll try to do both, yeah. So you'll know how you personally did, of course.
Nope, I did terribly. I think we got like halfway through it.
So there's a bit of a preamble. This is to do with selection. So from a selection sort, the number of comparisons. So selection sort effectively is just working at the maximum of what you got all the time. It's a pretty simple sorting mechanism. So it's counting the number of comparisons you do in a selection sort is given by that sum. And if you do a bit of trial and error, you can guess the formula is n times n minus 1 and 2. That's just so you can sort of guess the answer. Can you prove that it actually works all the time? And so that's what I'm going to try to do. I'm going to try to prove that particular result. Because it's something that's based on a counting number, induction's a really nice way of doing it. And in this case, in the assignment, you were told to do induction pretty much as well.
I was following through the way you did it in the lecture, and then I got stuck on the divide by 2 part, and I was just like, no, I don't know what I'm doing here.
Okay, so let's just have a go. So, you basically, how induction works, you need to have a starting point. So you want to consider a base case. So you want to consider the smallest thing which sort of makes sense. Now, it's actually a list. So if there was only one element in the list, how many comparisons do you do? If you had one element in the list, how many comparisons do you have to do work out how to sort it? Well, none. It's already sorted. There's only one element in it. So let's go. That's the boring case. Just ignore it entirely. So I guess the first case that's any interesting would be n equals 2. That's a base case we want to consider. So let's have 2 elements in there. And it may not be automatically sorted. You might have to flip the 2 to sort it out. So therefore, I want to work out the left-hand side and the right-hand side for both of those to see what I get. Now, they should be the same if it's going to work. If they're not, then I can say forget it straight away. So this is my left-hand side. Let's just look at a few things. It's summing up lots of terms. It's 1, 2, 3, 4. So just actually, the numbers, they're all just numbered quite nicely. So the number of terms would be n minus 1. So if I do n equals 2, there should be just one less. There should only be one term in the series, just one term. That's what I'm looking for. The way to work out what that one term is really just subbing n equals 2 up here. So 2 minus 1 gives you 1. And that's the only term, so that's it. The left-hand side is just the 1. The right-hand side, again, just plug in. So it'd be 2 times by 2 minus 1 all over 2. And that's equal to, hopefully 1, otherwise it wasn't going to work. So, result true for n equals 2. Now you can try to prove it n equals true for n equals 1 as well, and you get no terms at all on the left-hand side. That would be 0 is equal to 0. So you could do it for n equals 1 if you wanted to. This perhaps make a little more concrete sense for people. So that's the base case. The next thing you need to do is what's called the inductive step. So the inductive step pretty much says, I want to assume it's true for a particular value. So how I'm really going to do it, just think through stuff. So what I'm really doing is, I know it's true for n equals 2. So what I want to do is I want to use the inductive step to show that it's actually true for n equals 3. And when I know it's true for n equals 3, I want to use the inductive step a second time to prove it's true for n equals 4. And then repeat. So the inductive step really is just a way of going from one value of n to the next one. That's all it really does. But I don't want to do them all separately. I want to try to do them all in one go. So the inductive step is I want to assume the result's true for some placeholder. So that would be 2 or 3 or 4 or 5 or whatever I'm up to at this point in time. So I just use k as a placeholder. So I just write the whole thing down. So k minus 1, k minus 2, etc.
Yeah.
That's the placeholder. And if you're thinking about, that's going to be the different numbers we just plug in at any point in time. And then I want to try to prove for the next one along. So if I know it's true for 2, I want to see if I can prove it true for 3. Or if I knew it was true for 3, I wanted to see if I could try to prove true for the next number, 4. That's the basic idea. So I've got to know it's true for some number. I want to see if I can prove true for the next one. And the way to do that really is just start with the complicated side. So the left-hand side looks more complicated here because it's got lots of sums in it. And then try to simplify it. So for the left-hand side, I'm just going to copy into this form at the top, n equals k plus 1. So the top term would be k plus 1 minus 1. That would be that term there. And the next one along would be that minus 1 more. Etc. So I just plugged in here for the moment. And you go, well, whenever these things work, the k plus 1 minus 1 is going to be k, but this term here will match up to this one. So you can see there's lots of matching up to my original assumption, and that always happens for series. So when you get practice, you just go, oh, there's a nice matching up. So this next term is the k minus 1. And so all of those terms will match up to all those terms in the assumption. And as you get practice, you start recognising that's happening frequently. And therefore, that whole bit that I've highlighted in blue, it's going to be equal to k minus 1 on 2. And what I've done here is I've used the assumption. Now, what do we do next? Now, some of you guys know what to do, but at this point in time is those sort of steps are the simplest sort of step you do in every single induction problem. The next thing you do is just a bunch of algebra. Then you do algebra to equals the right-hand side. Pretty much what the rest of it's supposed to be. But I'll do it. But that's what you have to think through, and you go, so you have to write down enough to convince the mark you know what's happening. You can bluff your way through that sometimes. Like I can't always tell if you understand yourself completely or not, but you at least need to know what you're heading towards. So what I would do in this situation personally is I know the final answer has to be this thing here with k plus 1 in it. So it's supposed to be nicely factorised form. So I'll try factorising. So I factorise, put everything as a common fraction to begin with. So it's 2k plus k minus 1 over 2. At least it gets that all over 2 bit out for me. Then I know it's supposed to be factorised, so let's factorise it. So I can see it's a factor of k, both terms from top. So it's k times by 2 plus k minus 1. We're okay with that? So I just take a factor of k out. This is how I think about it. Now, there's not the only way of doing it. And I've got the 2 minus 1, that's just 1. So that's what I've got simplified down. Now, what I'm hoping to say, that's equal to the right-hand side. So now I should actually look what the right-hand side really is. So the right-hand side's supposed to be n equals k plus 1 times by k plus 1 minus 1. That's what it's supposed to be. And when I get there, I'm going to just sub to the original equation if you can't read anymore. K plus 1. Now, if I've got everything right, those should match up. Do they? You're going close enough? If they match up really well, you just go done. If you're going, oh, let's just make it really clear, how would I just swap the order so you can see more clearly what how the lines match up, perhaps? Just so everyone else is convinced that I know what is happening as well. So as soon as you get to that point in time, you go, therefore, and I'm going to write it all down, so the font's going to get really bad. Therefore, the result's true for n equals k plus 1, hence prove the inductive step. So since we have a base case and the inductive step, that would imply the result's true for n is greater or equal to the base case. So n is greater or equal to 2 is what we've proved it for in this case. So putting that conclusion down at the end is important. So that's induction. So just recapping, you have to write down base case at the top, had to do inductive step which involved making an assumption, then using the assumption to prove it's true for n equals k plus 1, doing some algebra in between, and then at the end putting a conclusion down to explain what it meant, which pretty much means the result's true for n equals greater or equal to 2. That's what I was looking for. The last one here was another proof. So prove by contradiction that if n is an integer and n squared is even, then n is even. So you could prove this using a contrapositive as well, but I say contradiction. So to do these sort of things, you have some premises and you have a conclusion. And it's really important to know which one's which, right? You need to be able to tell them apart just to be able to do this sort of stuff. So what you do for a proof by contradiction is we assume the conclusion is false. What's the conclusion? Well, it's n is even. If that was false, what would you have instead then?
N is odd.
Okay. So assume n is odd, aiming for a contradiction. That's what I do. So I got the premise. I'm taking the premises as given, and I'm assuming the conclusion is false, aiming for a contradiction. And I put that in just so people know where I'm heading toward. So what I'm trying to do is I'm trying to get that. So that's what I'm trying to aim for. I'm trying to say after a while that's absurd, that's silly, that's a contradiction. It's always false. That's what contradiction means. Remember, always false. So the premises are all about n squared. Let's muck around with that. So n is odd implies that n is equal to, say, 2k plus 1.